Welcome back. So last time we talked about the difference between displacement and distance, and the difference between speed and velocity. And the key thing is that velocity and displacement are vectors. They've got a magnitude, they've got a direction. So that means we've got to have three things when we're talking about these types of quantities. We need the direction, and if it's only one dimension, that's going to be positive or negative. We're going to need the quantity itself, the magnitude, and then we're also going to need to have the units on there. We also talked about how the position, the derivative of the position versus time curve, actually gives us the velocity. But when we looked at the example of the rocket robot, that velocity was changing. The slope of the line on the position versus time curve was changing. So what we're going to look at today then is, what do we call that quantity? Well, okay, we call it acceleration, but it might not mean exactly what you're used to thinking of. And so we're going to go into detail about that in the lecture to come. All right, let's get started. All right, so take a look in your books in the acceleration section. Now, as I said, the idea of acceleration is something you may think, oh yeah, I feel very comfortable with that. But what probably is going to cause some issues is the idea of this term deceleration. And I'm going to tell you on the front end, just wipe that term from your mind, Padawan. Deceleration doesn't actually mean much of anything. And in fact, it's very confusing for the kinds of things that we're wanting to do. So let's take a look at the diagram in your book here. And hopefully it'll be clearer on your own PDF. So here I've got a robot that's moving at some velocity to the right. If we apply an acceleration that is also to the right, that's going to change its velocity. Remember, this delta V means change in V, change in velocity. So as its velocity then increases as a result of this acceleration. So the new magnitude, and we're using the length of these vector arrows to represent the magnitude, the new magnitude is going to be longer. The robot's going faster. And that seems pretty simple, and that's probably what you think of when you think of the term acceleration. Now, I'm going to make one thing kind of explicit here. Remember, we always have to have a coordinate system, and that coordinate system needs to show us where the positive direction is. It also has a zero. In this case, we could set the zero anywhere that we want. You could put it where the robot starts or whatever. It has an orientation. We're going to make it flat. So in this case then, I've got a positive velocity that experiences an acceleration in the positive direction, and its magnitude increased. It went faster. And that probably makes pretty good sense to you. Okay, well, let's look down at this next case. This one probably also seems pretty familiar to you. So we've got a robot. It's got a velocity to the right, which again, we're going to draw our coordinate system in here. Always, always, always add your coordinate system. So we're going to say that's going to be the positive direction. So it's now got a positive velocity. Remember that the velocity is a vector, so it has to have a magnitude, it has to have a direction. All right, now we're going to apply an acceleration in the negative direction. So because the vector's in the opposite direction, then I'm going to be subtracting some velocity. That change in velocity that resulted from the acceleration is going to be in the opposite direction. And so the magnitude of the robot's velocity is going to get smaller. Okay, that's just a fancy way of saying it's slowed down. If I apply it, if I've got a robot moving in the positive direction, so it's got a positive velocity, and I've got an acceleration in the negative direction, the speed decreases. Now you probably called that a deceleration. And that may be okay until we get to the next situation. So let's move this over to the other side here and get it out of the way. All right, suppose I have the robot, and we're looking at this part up here. Suppose I have a robot that's moving in the negative x direction. So now we're going to draw our ground here, and we're going to have our robot going this way. So we're still going to make this be positive, right? But now it's got a velocity in the negative x direction. So our velocity is actually negative. Okay, now we're going to say that it has a positive acceleration. We're going to give it a positive acceleration. Now, if you remember from our last case, when we gave it a positive acceleration, then the robot sped up. And so we considered that to be an acceleration, right? Well, look at what's happening this time. Now I've got, when I look at my robot, now I've got an acceleration. We'll use the letter A for that because we need some sort of symbol. So now I've got an acceleration in this way. Well, that, remember, is my change in velocity. So my change in velocity is in this direction. My original velocity is in this direction, in the opposite direction, in the negative one. So what happens to the overall velocity once I'm finished applying this acceleration? Did it speed up or did it slow down? It slowed down. So just saying, oh, I've got a positive acceleration means I'm accelerating, a negative acceleration means I'm decelerating, doesn't actually work, does it? Here I've got a positive acceleration, and yet my speed, the magnitude of the vector is getting smaller. The same thing could happen with the next case. Let's take a look at microtask 1. So I want to draw on this diagram, I want you to draw some vectors showing the robot's initial velocity vector, its final velocity vector. So show the initial velocity vector on this first picture, its final velocity vector on the second picture. And then I also want you to draw an acceleration vector for which it has a negative acceleration, but it increases its speed. The magnitude of the velocity goes up. Pause the video, take a minute and think about this. I hope you thought about it, because sometimes unlearning what we've learned before can be harder than actually learning the material to begin with. So let's see if we can piece this together then. So we've got a robot and we want it to have a negative acceleration. All right, well, let's draw this way to be positive. We could easily do it in the other direction. That isn't necessarily going to make a difference. But if I have a negative acceleration, then I definitely want, get my picture back, there we go. I definitely want my acceleration to be in that negative direction. Now, if you chose to the left to be negative, that's fine. It just means your negative acceleration is going to be going to the right. Coordinate system doesn't matter as long as you're consistent. All right, but I want it to increase its speed. Well, this tells me that the change in velocity, remember that's what that means, the change in velocity needs to be in this direction. So my original velocity must be in this direction. It must be in the negative x direction. And then my final velocity vector then, so I took this, I added in my positive or my negative change in velocity. So my final velocity is going to look something like this. It's going to be bigger than this. The robot sped up. So here I've got a case where I have a negative acceleration and the robot speeds up. So could we call that a deceleration? Well, probably not. So the term deceleration doesn't actually mean anything to us. So instead, we always want to talk about an acceleration in the positive direction or an acceleration in the negative direction. That way it's always clear. So if I have, like I do in this case, the robot is moving in the negative direction, its velocity is negative, then if I add a negative acceleration, then it's obvious what's going to happen. It's going to speed up. On the other hand, what about in this case, as we saw, what if I add a positive acceleration? That's this case right here. If I add that positive acceleration, the robot's got an initial velocity in the negative direction. It's got a negative velocity. We add a positive acceleration, and the robot slows down. So as long as we're saying an acceleration in the positive direction, an acceleration in the negative direction, we're always going to get the right answer. If you say deceleration, it's, again, not clear what you mean. You certainly don't mean a negative acceleration, because sometimes that can make it speed up. So deceleration really is more talking about the speed, not the vector that's going in. But even then it's confusing, because as you can see, the speed itself depends upon the direction of the vector from that. All right, so what I want you to do now is look at the true-false questions in microtask 1, pause the video, think about each one very carefully, and tell me if it's going to be true or false. Pause the video. Really hope you went through all of this. These concepts, like I said, unlearning can be difficult. And so what we're trying to do with these microtasks is to ease you into that unlearning so that you can get the new learning when we're ready for it. All right, let's zoom in on this and take a look. All right, so if the robot's velocity vector is in the same direction as its acceleration vector, the robot's speed will increase. What do you think? No, that's obviously false, right? If my velocity vector is this way, for example, and my acceleration vector is in this direction, well then my final velocity vector is going to be longer. Same thing, if I'm going this way and my acceleration is in the same direction, then I'm going to have an even longer final velocity vector in that negative. So this one is definitely false. All right. If the robot's acceleration is in the negative direction, then the robot's speed will increase. Well, we've already seen an example of that, right? This example that we have right here, gave it the robot at the beginning of the microtask, this right here. If we gave the robot a negative acceleration, it actually increased its speed. So that's certainly not going to be true. And then, as you might expect from the other, we gave it an example where we gave the robot an acceleration in the positive direction. Let's take a look at this one right here. So if I have an acceleration, say, in the positive direction, we'll say that this is positive, and my acceleration then is going to be in that same direction. Then if my velocity is in this direction, is in the negative direction, well, then my final velocity is actually going to be less. So the robot's speed is going to decrease rather than increase. So that's not true either. Let's look at the fourth one here. If the robot's acceleration is in the positive direction, the change in the robot's velocity vector will also be in the positive direction. And that part is true. Remember, change in velocity is that delta v. And that's what an acceleration is. It's a change in velocity. So if the acceleration is in the positive direction, well, by definition, that change is also in the positive direction. So that one's true. If the velocity vector is in the same direction as its acceleration vector, then the robot's speed will increase. These last two are the key rules that you're going to want to remember. Although, again, if you draw your picture, it's going to be very obvious what's going on. Let me erase this so we can get some room here. Whoops, we don't need the ruler. Let's erase this to get some room here to draw. So if the robot's velocity vector is in the same direction as its acceleration vector, then its speed is going to increase. And this was the first case that we looked at, and what you think of probably being the normal case, where I have a velocity in this direction and I have an acceleration in the same direction, it's going to speed up. But what we've learned is that if I have a velocity in the negative direction and an acceleration in the negative direction, then the robot's speed is also going to increase. So this one is definitely true and is the best way of thinking about it. And then by the same token, this would be the opposite case. If the robot's velocity vector is in the opposite direction from its acceleration vector, then the robot's speed will decrease. So if I've got a robot's velocity this way and an acceleration this way, you see that my change in velocity, which is the acceleration, is in the opposite direction. So my velocity is going to get less. Same thing here. If I have a velocity in the negative direction and acceleration in the positive direction, then the change is going to be in the positive direction, and my speed, my magnitude of it, will get less. The robot will actually slow down. So this is why we say don't think about deceleration. It's just going to confuse you. You're going to get the wrong answer probably 30% of the time. Instead, think about an acceleration in the positive direction, acceleration in the negative direction, whatever that may be. Then we can always say, okay, if my velocity vector and my acceleration vector are in the same direction, its speed's going to increase. If they're in opposite directions, its speed's going to decrease. It's always clear. All right. Take a look on the next page then. Let's go ahead and erase this. Position things so we can see them here. There we go. All right. So take a look at microtest 2 here. So it says that we've seen that if the robot is moving with a constant velocity, then its position versus time curve will be a straight line, right? So constant velocity. So if I've got, let's go ahead and draw that. Let's just sketch that right quick. So if I've got position in meters versus time in seconds, then remember that the velocity was the slope of that line. If the slope doesn't change, well, then it must have a constant velocity. So the slope of that line is also, in this case, the instantaneous velocity, because it's not changing. It's going to be the same everywhere. Okay, so suppose the robot is traveling in the positive x direction and experiences an acceleration in the positive x direction. What's going to happen to its position versus time curve? Now we know that the velocity is increasing over time. So think about it. What's happening to the slope of the tangent over time? Is it increasing or is it decreasing? Okay. So in this half right here, so in this left half of the screen here, we're going to draw our position in meters and our time in seconds. Pause the video and let's see how you can do. Okay, so the best way to think about that is with the idea of a tangent. So my slope, the slope of my tangent down here, let's use a different color. The slope of my tangent down here might be pretty low because the robot starts off not going very fast. Now though, as we apply an acceleration, its velocity needs to increase. So maybe right here we get a slightly higher slope. And then it's going to increase again because it's still got that acceleration. So we're going to get a slightly higher slope, and so on and so on. And so if we kind of connect our slope lines here, I'm going to get a curve that looks something like this. And this kind of curve on a position versus time graph is characteristic of an acceleration. Anytime you see that kind of curve in your position versus time graph, then you can see that the velocity is changing in time because the slope is changing. And so if I see that, then I have an acceleration. And not only that, that acceleration must be in the same direction as the velocity. And in this case, my velocity is in the positive direction. You can see that because the slope is positive, right? So I've got this. In all cases, the slope is positive. And it's getting more and more positive, so therefore my robot must be speeding up. All right, now let's look at the next one. Suppose the robot's traveling in the positive x direction again, so its velocity is in the positive x direction. What does that tell you about the slope? The slope's got to be positive too. And it experiences an acceleration in the negative x direction. What is that going to do to its curve? So it's going to start out with some velocity, might be kind of high, and then we're going to apply an acceleration in the opposite direction, in the negative direction. Sketch this curve again. So let's go ahead and draw our shell, our shell here. So here's my position in meters, and here's my time in seconds. All right. Now, at the first, I've got a pretty decent velocity, right? So maybe I've got something that looks like this. If the acceleration, my velocity, as you can see, is positive slope, moving in the positive direction, right? Just keep saying these things to yourself. Walk through it each time. So I've got a positive slope, velocity's in the positive x direction. Now I'm applying a slope or an acceleration in the opposite direction. What did we decide that's going to do to the speed? The robot's going to slow down. Its velocity, the magnitude of its velocity, which means the slope, is going to get less and less and less. So let's kind of try to sketch what that might look like. So here I've got this, and then I've got this, and then it's going to get maybe a little bit less and a little bit less. And so here, if we connect our lines, you can see that you get a curve that looks something like this. Now, once we hit here, what is the velocity in this region right there? Well, the slope is 0. So do you see that the robot's position isn't changing? So here I had a robot that was moving, and it went slower and slower and slower, and then finally stopped. And so for all time at that point then, it just keeps going, stays in the same position. Also though, the slope of the line, which is the velocity, is 0. So when we start using these graphs and we start thinking, okay, my robot's moving forward and I want to slow it down, well then I may apply some brakes, there may be friction present, any of this sort of thing. But I'm going to see that curve because the robot is not simply going to go something like this where it's got a velocity and then it doesn't. That's not possible. You can't get this instantaneous change. Instead, I'm always going to get this typical curve that kind of looks like this as I finally slow down to a complete stop. All right, so that change in velocity then, that's our acceleration. So when we talk about acceleration, that's what we mean. It is a change in velocity. It's a delta V for that. All right, so just like we did before, we can define the average velocity to be, and we've got it right here, but I'll make it big. The average velocity, remember it's a vector, we're going to define that to be the change in velocity. However, if you think about it, I could have that velocity change really, really slowly. And that means I probably have a fairly small acceleration. On the other hand, if that velocity is changing very quickly, well, now I've got a very high acceleration. So it matters the rate at which I'm doing it. So we'll put in that delta t. So just like the rate at which my position was changing in time, the rate at which my velocity is changing in time gives me my acceleration vector. All right, anytime we define a new symbol, we need to know what its units are. So take a look down here at microtask 3. We're going to use this same technique, So I want to know, what are the units of velocity? Well, I have to have the same units on both sides of the equation. So on this side, I don't know what it is. That's what I'm trying to find out. So what are the units of velocity? Well, those are meters per second, because remember, we're always going to put everything in meters, seconds, and kilograms. What are the units of time? Okay, pretty obvious there. That's going to be seconds. All right, so if I look back at my expression here, I've got meters per second divided by seconds. So the easiest way to do this, if you think about flipping and multiplying, get the camera back, there we go. If you think about flipping and multiplying a fraction, that's how we divide, right? So I've got meters per second times, I'm going to flip this seconds, I'm going to flip the seconds, then it will go in the denominator, because I'll make this a 1 over s. So now when I multiply it, then I get meters over seconds times seconds, which is seconds squared. So the units of acceleration then are going to be meters per second squared. Now that may seem weird, but let's interpret that. This means the rate at which the velocity is changing. So in this 1 second, my meters per second is, my velocity is this. In the next second, my meters per second, my velocity is this, and so on and so on and so on. So don't get too confused by the fact that there's a seconds squared. It doesn't mean I'm actually squaring the time or anything like that. It's just the rate of change of the velocity. And I could just as easily write my unit as this, but the other way is much more compact, and we're lazy. So that's what we're going to do. All right. So look on the next page. So let's suppose then that we want to measure the robot's acceleration from this position and time graph. So here we've got a battle bot, and it's going to drop a rock on its hapless opponent and try to crush it into nothingness, because that's cool. We actually want to destroy what they've got. So how would we get the acceleration from that position and time graph? What I want you to do is pause the video and think about that for a minute. Let's see if you can figure out a way that from the position versus time graph. So if I have my x in meters and my time in seconds, how could I measure the acceleration from that? We already know what the curve looks like, so how can I measure that? Okay, so have you thought about it? All right, well, so here we've got the same situation that we had before with a rocket robot. Here we're dropping that rock, and we're taking pictures with our high-speed camera, so every 500th of a second we're going to take a picture. And so that's what you're seeing down there. Now, just looking at the spacing between these, do you see that because the time from here to here is the same as the time from here to here, but it traveled faster, it traveled further. So that means that it's traveling faster, right? Its velocity went up. And then it's the same amount of time to here, but I traveled even further in that time interval, and then even more here. So you can see that my velocity of the rock as it falls is going faster and faster and faster. Maybe you know what's causing that, but we'll get to that later. All right, so here's the data that we took from that. So what I want you to do is pause the video, and I want you to plot the position versus time on the graph that you have there. So plot that position versus time. It's going to be a good way for you to understand what's going on. Pause the video, do that now. Got it done? Now you really do need to do this, okay? It's very important. Well, we already know what our graph should look like, just, in general terms, but now we want to actually get precise with it. And so if you were to plot it, you'll get something that maybe looks something like, I'm just going to sketch it, but it's going to look something like this. And that's our characteristic acceleration curve from that, okay? So is the velocity, look down at the questions here, you can see that the velocity is getting more positive, and the speed of the rock is going to be increasing. We've talked about this before, right? So the slope is increasing because it's becoming more positive, and so the speed of the rock is also increasing. All right, look on the next page. And let's erase our straight lines here. Now, up to this point, we have only been talking about position versus time curves, but we can also do a velocity versus time curve. So you could take your graph and you can measure the slope of tangents. You can take a tangent at each one of those time markers for the photo. Why don't you pause the video and see if you can get kind of a rough estimate of what that's going to be. Have you got it? Okay, now you may not be as precise as I'm being right now, but that's okay. So I'm just going to do to basically one significant digit for this, maybe two as we get further along. So I got a slope here of positive 0.5 meters per second. Remember, I don't have to write my units if my column is labeled. I do, however, have to have that sign there. I have to have the direction because it is a vector. Then at photo 2, I got that the slope of the tangent was 1.0. Remember, the slope of the tangent is the instantaneous velocity. If I had an equation for my x versus t curve, if I'd already done a fit to it, well, then I could take the derivative of that and get these numbers directly. So far, I don't have that. All right. Then here at photo 3, I got positive 1.5 meters per second. I think you're probably starting to see a pattern. This was 2.0 and this was 2.5. So every 500ths of a second, my velocity went up by 0.5 meters per second. So if we're going to graph that then on this velocity versus curve, notice that this is a velocity in meters per second. And then I've still got my time in seconds. So I'm going to get something that looks kind of like, I'm not being very careful with how I'm plotting this because I'm just going to sketch it. I'm going to get something that looks kind of like this. And so you see that it's going up at a steady rate. For every 500ths of a second, the velocity increased by 0.5 meters per second. And when I plot that on the velocity versus time curve, I get a straight line. So, scroll up here so we can see the picture then. Yeah, so it says, what do you notice about the slope of the velocity? Well, it's constant. It's not changing at all. There's no difference in it. Can you see that? Now remember, when we looked at, had a straight line in our position versus time curve, that told us that the velocity was constant. What do you suppose this is telling us about the acceleration? Because remember, the slope of this line then, if we're going to write that out, and we're going to do that in the next microtask, but you've got a block for it on the next page, but I'm going to go ahead and keep it on this same page. The slope of our line, remember, it's going to be the change in our vertical component here, which is the change in velocity, and divided by the change in the horizontal component, which is going to be the change in time. So that's our slope. That's our geometric slope. Well, look at this. We've already defined that to be our average velocity. So the average velocity then is the slope of the velocity versus time curve. The velocity is the slope of the position versus time curve. But if I figure out all my velocities and if they're changing, then I'm going to get a constant acceleration. If the velocity were not changing, the robot could still be moving, but it would just simply have an acceleration of 0. And in that case, let's do this in a different color so we don't get confused. Maybe I was moving at some velocity here and it simply didn't change. Well, the slope of that line is 0 and that tells me the acceleration is 0. But it doesn't mean that the velocity is 0. Okay. All right. Now let's flip over to that next page and let's look at the next microtask. We'll erase what we've got here to get rid of all the extra stuff. All right, so remember our rocket-powered robot that we had. So we were able to calculate the instantaneous velocity at all the points. And we found that the slope of that line, or the equation for the position versus time line, this was the best fit equation, was 10.9 t cubed, right? So if I plug in 0.5 into this equation, for example, I should get 0.001. I should get what my final answer is in there. So how do I get my velocity versus time curve? Remember? So if I want the instant, I have to take the derivative of that. So I have my x is equal to 10.9 t cubed. And remember, if I take the derivative of both sides, and we did this in the last lecture, so none of this is new. Like this, I take that derivative with respect to time, and then delta dx dt then is the instantaneous velocity. Remember, if I don't put a subscript here, then I mean the instantaneous velocity at that specific time t. We'll go ahead and make that a function t for this one. And then I take the derivative of this, and remember that that was 32.7 t squared. So that was my equation for my velocity versus time. Now what you can do is you can go back and fill in this chart without having to do any measurements. You simply take your time, plug it into this equation, and you'll get the velocity. Pause the video, take out your calculator, definitely do it in a calculator, and run through that right quick. Got it? Gonna need it because we're gonna need it for the next step that we're doing. Okay, so if we do that, and I'm gonna just look at my notes for this, I got 0.0818, sorry. I got 0.0818 meters per second for the first velocity, and then the instantaneous velocity for point 2 was 0.327 meters per second. The next one was 0.736 meters per second. Then now it's going to be, let's get that out, it's going to be, get my color palette out of the way, fine. 1.31 meters per second. Go on, check, make sure that you're getting all this. You remember we wanted it at 0.5, at 5, it was 2.04, and then 2.94, 4.01, 5.23 meters per second, and 6.62 meters per second. But we're not finished. What is missing from this column of numbers here? It's a vector. So we've got the magnitude here, but we also need the direction. What direction was it? Our t was positive. So the direction in this case is also positive. So we're going to go back through and we're going to make all of these positive. Just like that. All right, now look on the last page then. You could take that and you could actually plot all of those numbers. So let me move this to the side and then erase our extra numbers here. So go ahead, I'm going to remind us what our velocity was here, our velocity equation. Our v of t, and that's a vector, is going to be equal to 32.7 t squared. All right, so pause the video now and plot all of your velocities with respect to time, because what we've got here, remember, if you take a look at the graph, we've got the velocity in meters per second that we're plotting versus time. So let's do that. Pause the video, make it happen. The reason it's so important that you plot this is for what you're about to see here. When you plot this, you should get, and you connect your lines, you should get something that looks something like this. Remember how we said that this was not linear, but it is a quadratic. Do you see that that matches the form of our VT, of our velocity with respect to time? Quadratic means it's raised to the second power. And so that actually matches our equation. So this gives us exactly what we would expect to find. So if I didn't have my individual numbers, all I had was this graph, I would immediately know that I had a quadratic from this. And when I do my curve fit, I don't want to do a linear fit because you, the human, have to decide. The computer doesn't know. I wouldn't want to do a linear fit here. I would want to do that quadratic fit. And then it would give me this equation right here directly from the graph. Right? Does that make sense? Do you see where we're going with that? Okay, so we've just got really one more topic that we want to cover here, and then we'll be done for the day. Again, let's erase what we have here. Now, we talked about how the slope of the line then was going to be, the slope of the velocity versus time curve was going to give me my average acceleration. But remember that average, I had to take it over 2 different points. How would we find the instantaneous acceleration? Well, the technique is exactly like what we did before. So I'm going to take the limit as delta t goes to 0 of my average acceleration expression, which is delta v over delta t. And remember, this means change in velocity divided by change in time. Well, hopefully you recognize this as being the derivative of the velocity with respect to time. And that is defined to be my instantaneous acceleration. So just like my instantaneous velocity was the derivative of the position function with respect to time, my acceleration is the derivative of the velocity with respect to time. So what if we don't have an expression for the velocity to take the derivative of? So what if we only had, let's say we didn't have that velocity fit that we had before, and we've only got our position fit. Can you come up with an expression for the acceleration? Well, we know how to do that. You just take the derivative to get vt, and then take the derivative of the v of t to get a. So we just do it twice. So let's go ahead and do that. You do it in this space, and then I'll do it over here. All right? So we start off with x of t is equal to 10.9 t cubed. To get my velocity, that's going to be a vector, to get my velocity then, I'm going to take the derivative of this, and we already saw that that gave 32.7 t squared. Now we're going to take the derivative again so that we get the acceleration. So the acceleration, again, is a vector with respect to time. We're going to take the derivative of that, so it's going to be 2 times this number. And, you know, as always, don't trust my math, but when I did it, I got 65.4, like that. And then I reduced my exponent by 1, so I have 65.4 times t. Just a side note here. You notice that I put little curlies on my t's. That's so they don't look like pluses. So if you see a curly, that's a t. If you don't see a plus, then that's, if you don't see that curly, then it's a plus mark. All right. Okay, so that's it. That's my expression for my acceleration as a function of time. And I didn't have to actually mess with the graph more than once. I messed with the graph to give me that equation right there because maybe that's what my sensors were giving me. If you're working with the robots, they will often have an ultrasonic distance sensor that allows you to get the position. So many times that's all you have when you're working with the robot. So I get my position versus time graph, but now I can actually calculate the acceleration and how that's changing with time for that. All right, so using this then, take a look at our last expression, or our last page that is, and we'll erase the extra stuff here. And you should be able to fill in this table simply by using our expression. So we got that the acceleration was, as a function of time, was going to be equal to dv dt, but v was the derivative of x with respect to time. So I could also write this as the second derivative of the position with respect to time, and that'll give me exactly the same thing from that. So we did our math, we got our work, and we said, okay, a of t, which is a vector, was going to be 65.4 t. This curve is linear. You see that it just varies. It has the form of y equals mx plus 0 in this case. So that means it's linear in t. So we should be getting a straight line. And that's exactly what we got when we plotted our velocity versus time. So in this case, though, it's my acceleration that's changing. So now I've got my acceleration that's changing with time instead of just my velocity. So not only am I going faster each time interval, the rate at which I'm going faster is going faster. This is a rocket engine. Think about our rocket robot. When we throw out that mass, then we've got less mass we need to push, so for the same oomph, we get a bigger velocity change. So as that decreases, then my acceleration is going to actually increase. Now with a real rocket, it actually is a logarithm, and we'll get into that later on, but even so, you can see that the acceleration is going to be increasing in this point. So you can take those pictures, you can plug them into your equation then, and you should be able to get your numbers. Pause the video, let's do that right fast. All right, ready to go? Let's drag this down where we can see it. All right, so this is for our rocket robot that we were talking about before, not the dropping rocks, but our rocket robot. And so when I did this, I got positive 3.27 meters per second. I got meters per second squared because it's an acceleration. Positive 6.54 meters per second squared at photo 2. And then 9.81 meters per second squared. That might be a familiar number to some of you, but we'll talk about that later. And then positive 12.1 meters per second squared at photo 4. By the time we get to photo 5, the robot's acceleration is 15.4 meters per second. Think about what that means. Not only is the robot's velocity increasing, but the rate at which the velocity is increasing from that. Okay. And so then continuing on with photo 6, that's going to be 19.5 meters per second squared. 7 is going to be positive 22.9 meters per second squared. 8 is going to be positive 26. That's a 6, I promise. 0.2 meters per second. And then finally, number 9 is going to be positive 29.4 meters per second. See if all that matched up. All right. Now, there's one more thing that's not on your page, but I do want to make a brief mention of it. Let me get this out of the way for us. And we'll just erase this. What if I have the velocity, but I want to know what my position is? So let's say that I know that my velocity versus time curve, we'll use the one that we used before, we got 32.7 t squared. Now, we know what the final answer is. We know that we need to get the 10.9 t cubed. Same thing that we did before, same thing that we did last time, we're going to integrate both sides. And so I'm just going to briefly repeat that. We did this last time. And so I get dx dt is going to equal integral 32.7 t squared. Bring my dt's to the other side, so dt dt. I get the integral of dx equals integral 32.7 t squared dt. Integral of the differential is just the symbol, so that's going to be that. And then if I raise this to the third power, I'm going to have to divide by 3 here, and again, finally I'll get my 10.9 t cubed. I also, though, have c. And this is something we haven't talked about up to this point, but remember how when I had to find my initial conditions from x of 0. And so I put in my 0 here into time 0, and I get that my x position at time 0 is going to be equal to that constant, whatever that may be. Okay. So if I have the velocity, we know, as we saw last time, we can integrate and we can get the position. If I have the velocity, I can take the derivative and I can get the acceleration. So keep up with which direction I'm going, and you'll be able to take any one of these 3 expressions and get what you need. Let's say that all I'm given is the acceleration. We're going to do problems where that's true. And again, we'll keep the same acceleration that we had before. It was 65.4 t. So if I have this, then how will I get the velocity expression? We're going to integrate both sides, right? Because I need to go backwards. I took the derivative to get here, so I'm going to take the integral to go up. Let's put this over here where we can see it. So I have the integral of dv dt equals the integral of 65.4 t. Multiply both sides by dt, so they cancel. And I get integral of dv, these are vectors, equals integral of 65.4 t dt. And so my velocity as a function of time then is going to equal, if we do our math here, we're going to get back to our 32.7 t squared plus a constant. And you see that we didn't have that constant before, but I still have to specify what are my initial conditions. Well, if you look at your original velocity versus time curve that we worked with before, which we derived again, this was equal to 32.7 t squared. Well, at t equals 0, the velocity was 0. So we happen to know for this case, my initial condition was 0. And so if, remember we solved this by putting a 0 in here, so I get v of 0 is equal to 0 squared times 32.7 plus c. So my initial velocity then will always be equal to c. And in this case, what we've been working with, we've been saying, well, my initial velocity is just 0. All right. Well, now that I've got this expression, now we can come back over here, and then we can integrate it and get our position as a function of time. So if I know any one of these expressions, I can use calculus to get the other 2. And that's the main thing that we want you to take away from this. Okay, so you should now have some idea of what we mean when we talk about acceleration. There's 3 main things that I want you to get out of this lecture. First of all, deceleration doesn't exist. That's not a word that tells you anything helpful. So you may as well just get rid of it out of your vocabulary, never use it again. We always talk about an acceleration in the positive direction or an acceleration in the negative direction. Because then if you know the direction of your velocity, well, now you know what's happening with the speed. deceleration, you might could say, okay, yeah, that's my decrease in speed, but that still doesn't tell you whether the acceleration was coming in the positive or the negative direction. And remember, it's a vector, so you actually have to know what that is. Second thing is we want you to be able to read the acceleration off of a velocity versus time graph and off of a position versus time graph. So know those characteristic shapes. Remember the position versus time graph, it's going to be this increasing slope as it goes up, or decreasing slope if it's in the opposite direction from the velocity. And then on the velocity graph then, if it's a constant acceleration, it'll be a straight line, but it doesn't have to be. Remember with the rocket, that could also be something that's changing in time. So you should be able to look at any velocity versus time and any position versus time and tell me physically what's happening to the robot. If you were actually physically looking at it, what would it be doing? And then the final thing is we discovered that the instantaneous acceleration is simply the derivative with respect to time of the velocity expression. And since the velocity is the derivative of the position expression, then we could also say that the acceleration is the second derivative of the position. So all of those pieces, if you put them together, will allow you to determine the acceleration anytime you need it. Now, just a preview, later on we're going to learn that that acceleration is always caused by something, that oomph that we talked about. That oomph is really a force. But we won't be dealing with forces for quite some time. We're going to move into, first of all, we're going to talk about describing the motion. Remember, that's our kinematics. So we're going to say, okay, now that I've described the motion and can I predict what's happening, then I'm going to say, okay, can I see what's causing that motion? That's the dynamics part. So if I know the cause, I know how it's going to behave at some time later. So we're building it up step by step, and you're going to be able to get all of this by the time we're done. So if you've got any questions, be sure to let me know. We'll see you next time.